All right, the next example just shows that acceleration can be negative. This is a good one. All right, let's skip to this one. A ball with a speed of 10 meters per second is thrown perpendicularly at a wall. After striking the wall, the ball rebounds in the opposite direction with a speed of 8.0 meters per second. If the ball is in contact with the wall for 0.012 seconds, what is the average acceleration of the ball while in contact with the wall? All right. Again, we're going to need to do some erasing and get a new diagram. Now, here's the thing about it, okay? You may have already started drawing a diagram to do this one, or you may have just decided that Mr. Hamilton's going to do it for you and you don't need to. So, either way. All right? I can do this either way. I can set up my reference frame with positive and negative. I can set it up with negative and positive. Notice that it gives me speeds too. A ball with a speed of 10.0 meters per second is thrown perpendicularly at a wall. And it rebounds in the opposite direction with a speed of 8.0 meters per second. Now, if this were a free response question on a test, it really wouldn't matter which reference frame you chose. It wouldn't matter what you chose for the initial, just so long as you are consistent with it. Okay? I'm even going to go a little bit unconventional with this. No, on second thought, I'm not. I'm going to go regular conventional on this. Right? So here's a wall. And the ball is initially coming to the wall with a speed of 10.0 meters per second. It's going to strike the wall and rebound the new velocity of, well, mind you, again, they gave us speeds, we need a velocity. It looks like I've already chosen to your right as positive 10.0 meters per second. So when it rebounds in the opposite direction, its speed is 8.0 meters per second, but its velocity in our reference frame is negative 8.0 meters per second. And then lastly we have, well, they've given us the time. If the ball is in contact with the wall for 0.012 seconds. So we know that the time it's in contact with the wall for, right, when it hits the wall, that's something going, right? Okay. Delta t, 0.012 seconds. Can you see that? Yes, just made it. All right. So what we want to know is what is the average acceleration of the ball while in contact with the wall? Well, we can see here, even before doing any calculations at all, that the acceleration is going to have to be negative. Right? What direction does the velocity of the ball change in? The ball is initially going in this direction, and then afterwards it is going in this direction. So the velocity changes in this direction. We should definitely expect a negative value for our acceleration in this case. All right? And that's just what we'll get. Now, you'll notice that we're given kind of a mixture of variables here. In order to solve this, we're not using delta v and delta t right off. We're going to do something that looks more like a hybrid of it. All right? So I'm going to change delta v into v2 minus v1. But delta t, well, they kind of already told us delta t. It's in contact with the wall for a delta t of that much. So we can just put that in there. The rest is just putting in some variables. We're going to go negative 8.0 meters per second minus positive 10.0 meters per second over 0.012 seconds. We should expect a pretty large number in this case, and that's just what we get. Hang on, sorry. I don't know. I was going to do this with my calculator, but got it. It's about negative 1,500 meters per second squared. All right. Now, one last example to show you how we might use these equations a little bit differently. I hope by now that you are starting to see equations as sort of a very fluid thing that you can really manipulate according to the laws of algebra, that you can manipulate for your own ends in this case. Alright? And it's mathematics, so it has no feelings. You're not doing anything wrong by manipulating it. Don't manipulate humans or animals or any other sentient being. I don't know where robots are fitting into that these days, AI being what it is. Okay? One more example before we go. Let's take